session will be performed by Yuki Ishizoma, Tomoya Kawabata, and Shu Aizuma. It is entitled "The Development of Simplified Evaluation Methods of being Characterized Toughness in Small Scale and
use this script. Hello everyone, my name is Yuki Nishizono from the University of Tokyo in Japan. Today, I'd like to talk about development of simplified evaluation method of brittle crack arrest toughness on small-scale bending test in steels. This is a brief outline of my presentation. First of all, I'd like to talk about the background of my research. This figure shows the historical transition of container ship carrying capacity. Generally, container ship with larger carrying capacity are advantageous in transportation cost. Larger container ships have been designed and constructed increasingly. As shown in this figure, container ships are designed to have a hatch opening for convenience of loading and unloading. The hatch side coaming assembled at the deck is an important structural member for securing their strength against wave load, and it needs to be a thicker steel plate for larger container ship. Brittle fracture is likely to initiate in heavy thick steel plate with low fracture toughness, which may lead to catastrophic failure such as hull breakage. Therefore, in order to avoid such an accident, it is one of the solutions to prevent crack propagation even if brittle cracks are initiated. Fail-safe design concept has become common in recent safety assessment, which requires crack initiation prevention and crack arrestability. It is common to conduct a wide plate tensile test, such as S-test. As an example, the testing concept of S-test is shown in this slide. S-test was developed by Standard Oil Company in response to the two oil tanks failure caused by brittle fracture. Also, S-tests make it possible to accurately evaluate arrest toughness, which indicates the Arrhenius type temperature dependence. It is not suitable for quality assurance tests at mass production of steel plates due to its high economical cost and long lead time. Many small-scale tests have been developed for evaluating arrest toughness easily at low cost. As an example, the test concept of press-notched bend test is shown in this slide. In 2015, the Japan Welding Engineering Society proposed and standardized this test as a simplified method to evaluate arrest toughness in steel material. In this test, arrest toughness KCAPB can be evaluated by static calculation formulas, which is represented by fracture-initiated load, arrested crack length, and specimen size. Evaluation result by S-test and press-notched bend test with same steel are shown in this figure. As you can see, KCAPB deviates significantly from KCA evaluated by S-test in the Arrhenius type temperature dependence. The affinity of both evaluation methods is to evaluate arrest toughness based on the magnitude relation between crack driving force and crack propagation resistance. Thus, in order to evaluate KCA accurately by smaller scale bending test, I applied a dynamic stress intensity factor calculated by 3D elastoplastic FM model and aimed to develop simplified evaluation method combining economic efficiency characterization based on fracture mechanics and correlation with S-test. Next, I'd like to talk about two types of steel plate used in this research. Steel A was used in the preliminary experiment introduced in Chapter 3, and steel B in the main experiment introduced in Chapter 4. These tables show chemical composition and mechanical properties. The configuration results shown in this table were applied as the input data of FEA. In this chapter, I'd like to talk about the preliminary experiment. To determine the appropriate test specimen design, I analyzed the relationship between test specimen shape and dynamic crack driving force by a number of FEAs, in which the input data, such as crack front shape and crack velocity, are assumed to be constant, and crack driving force varies with crack propagation. Such a simplification was considered valid in terms of connectivity with abundant existing data and harmonization with conventional approach. Crack driving force in arbitrary position is calculated by fitting opening stress distribution to linear elastic fracture mechanics theory. Test specimen shape affects the tensile compressive stress distribution at brittle crack initiation and hence KD transition. This figure shows the typical KD transition of the press-notched bend test, which was calculated as previously noted. According to the past research, it was pointed out that KD tend to decrease at the high rate in the top side of the specimen, where the precompressive stress field is formed by bending load. Such a tendency qualitatively agree with the frequency of crack arrested position. To sum up, the static calculation formulas may not be able to accurately characterize the dynamic crack driving force. As a result of analysis on the relationship between test specimen shape and KD, it was confirmed that KD monotonously decreases when the compressive stress field in the top of the specimen is enhanced. Next, I'd like to talk about the preliminary experiment results. Test specimen used was a small-scale tapered specimen with 5 mm depth press notch. Temperature of test specimen was kept within the aimed temperature plus or minus 2 degrees Celsius for at least 10 minutes in ethanol and frozen carbon dioxide. Brittle cracks were initiated and arrested in all 14 test specimens. This slide shows a photograph of fracture surface, brown colored by heat tint after the experiment. And the longest crack lengths from the notch tip were measured as arrested crack lengths. This table shows all of test condition and the results. Several test results are considered invalid because the specimen showed too large deformation and ductile crack before brittle crack initiation. However, test temperature and arrested crack length of valid result have a strong relationship, as shown in this figure. This result suggests that the crack driving force decreases monotonously with crack propagation. Then I evaluated arrest toughness at each test temperature by applying the test results. This slide shows the generals of dynamic 3D last plastic FEM model simulating the preliminary experiments. Brittle crack propagation is simulated by the nodal force release method, and the nodal force along crack front decreases linearly to 0 in each step of time. This method is called ramp method. The crack velocity is assumed to be constant and the crack front shape is assumed to be flat. This analysis outputs the opening stress in the vicinity of crack tip at the thickness center. These figures show the KD transition with crack propagation. For all analysis results, I confirmed that KD decreases monotonously regardless of crack velocity. KD, when the brittle crack were arrested in the experiment, is defined as KD critical, which characterizes arrest toughness at the test temperature. Then, this figure shows the evaluation result of KD critical in the preliminary experiment and S test. Both data have a high extrapolated correlation. Because the result obtained from the preliminary experiment seemed successful, we proceeded the enlarged experiment in order to obtain higher KD. This is denoted as main experiment in my talk. Test specimen used was a tapered 3-point bend specimen whose planar size is 4 times the preliminary experiment. In order to avoid ductile crack initiation at the high test temperature, test specimen after the press notch processing were applied a slight 4-point reverse bend. This table shows all of test condition and result. Brittle cracks were initiated and arrested in all 3 specimens. According to the temperature measurement result, temperature of test specimen can be controlled accurately in this test with no temperature gradient. As in the case with the preliminary experiment, I evaluated arrest toughness at each test temperature by applying test results. These figures shows KD transition with crack propagation. For all analysis results, I confirmed that KD decreases monotonously regardless of crack velocity. Considering the maximum value of KD, it can be said that unless toughness of at least 6,000 can be evaluated by this test. Then, this figure shows the evaluation result of KD critical in the main experiments, and KCA evaluated by S-test. Both data evaluated with same steel have high correlation. In other words, this result suggests that KD calculated by simplified 3D elastic plastic FEA can accurately characterize the physical property of KCA evaluated by S-test. Finally, let me summarize the findings obtained in this research. A groundbreaking evaluation method of brittle crackers toughness on small-scale bending test was developed in this study, by which we can evaluate KCA of at least 6,000 accurately. And this evaluation method needs relatively small test load, short lead time, small accumulation data, and simplified elastic plastic FEA. It can be said that this evaluation method may cover the needs of a wide range of industrial fields, not only container ships, but also nuclear, tank, hydroelectric power plant. Future task is to express KD transitions on different test conditions as a function in order to omit some simplified elastic plastic FEAs. Thank you all very much for your attention.
So, please, some question? Please.
So, what do you think are the challenges with testing these small specimens?
Once more, please.
What's the challenge? What is the main reason why doing this test?
That is why this is a conventional press notch bend test. This is a KD transition of conventional press notch bend test. This KD in press notch bend test is increasing in the bottom of the specimen. So in this area, the brittle crack is not likely to be arrested. So in a new simplified evaluation method, KD tends to decrease monotonously in the specimen. So
Okay, maybe if I mean that when you are doing the experiments with those small specimens, what do you think is from quality point of view? What are the most problematic issues? Like, you mentioned plasticity.
yes.
It causes problems, and what was the other one? You had some ductile crack growth. How in the specimen? You said that you had ductile crack growth in the specimens.
The size effect of your results. You could have different size with different results.
The result of the main experiment are the result of S-test and result of tapered press notch bend is evaluated in same thickness with same steel. Both data have high correlation. So this test is beneficial in accuracy, evaluation accuracy.
So, one short question more. Okay, if somebody has question, we can ask. This is now the end of our section. As you know, the commission in the members are Professor Dragan Kozak from University of Josip Juraj Kostromel,